Welcome to Paper Trail, where we make academic research accessible and engaging. Let's see what the evidence says. For years, when we thought about AI coding assistants, we pictured something tucked away in our IDEs, maybe suggesting a line or two. But this paper on OPENDEV describes something entirely different, an autonomous AI agent that lives right in your terminal, and it's built to tackle complex, multi-step software engineering tasks all on its own.
And what's truly striking is its ambition for long-horizon development tasks. This isn't just about code completion. It's about an AI reasoning, planning, executing, and even self-correcting over hours or even days in the very environment developers use for source control and builds.
It almost sounds like a developer pair programming with an invisible, incredibly fast colleague. But in the terminal, that feels counterintuitive to me. I thought the terminal was for quick commands, not deep, complex logic.
And that's precisely where the terminal revolution comes in. The authors argue that the command line interface, far from being a limitation, is actually the operational heart of software development. It natively supports the exact primitives an autonomous agent needs: shell commands, source control integration, build systems, remote SSH sessions. It's a universal, powerful, and often overlooked canvas for AI autonomy.
So instead of being constrained by an IDE, it's leveraging the raw power of the underlying system. That makes a lot of sense. But if it's operating with unprecedented autonomy directly in your terminal, executing arbitrary commands, the first thing that jumps to mind is safety. How do you stop an autonomous AI from accidentally wiping your hard drive or pushing half-baked code to production?
That's the million-dollar question, and it's one of the most rigorously engineered aspects of OpenDev. They don't just rely on a single checkpoint or a polite "are you sure" prompt. Instead, they've built what they call a defense-in-depth safety architecture with 5 independent layers.
5 layers? That sounds serious. Can you walk me through them?
Absolutely. The core lesson here, which I think is a significant takeaway for anyone building agentic systems, is to make unsafe tools invisible, not blocked.
Wait, invisible, not just blocked. What's the distinction there?
It's fundamental. If an AI model sees a dangerous tool in its schema, say a command to rm-rf/, it can still reason about invoking it. It might try to argue for why it should be allowed, or even probe for edge cases in your permission logic. It still knows how to do it. But in OpenDev, for tasks where destructive operations are inappropriate, those tools are literally removed from the agent's available tool schema. The planning agent, for instance, operates with only read-only tools. It simply doesn't have the option to write or delete. It cannot attempt writes because it never sees a way to invoke them. It's structurally impossible, not just a policy check.
So it's not just a guardrail. It's like the road simply doesn't exist in that direction. That's incredibly elegant. What are the other layers?
Beyond that schema-level restriction, you have runtime approval systems, which can be configured for various autonomy levels: manual, semi-auto, or fully auto. But even with auto approval, there's an approval rules manager that evaluates commands against prioritized rules. Think of patterns like rm-rf or changemod 777. These are hard-coded to be auto-denied at the highest priority, no overrides.
So even if I, the user, accidentally set it to auto-approve everything, some truly catastrophic commands would still be blocked?
Precisely. Then you have tool-level validation, which includes things like stale read detection for file edits. If the agent tries to edit a file that's been modified since it last read it, the edit is rejected. This prevents silent overwrites of concurrent user changes. And finally, there are lifecycle hooks, which are user-defined scripts that can intercept tool calls, even mutating arguments or blocking execution entirely. It's a robust, layered approach where a failure in one layer doesn't compromise the others.
That's truly a comprehensive approach to safety. It shows a deep understanding of the potential failure modes when you give an AI this much power. But beyond safety, what about the inherent limitations of LLMs themselves, especially their attention span? We know context windows are finite, but long horizon tasks, by definition, accumulate a massive amount of information. How does OpenDev prevent its AI brain from getting overwhelmed?
This is where OpenDev really shines, treating context engineering as a first-class concern. They've implemented a fascinating array of techniques to manage the LLM's finite context window, starting with something they call adaptive context compaction, or ACC.
Adaptive context compaction. Is that just another way of saying summarize everything when it gets too long?
It's much more nuanced than that. Think of it like a smart, multi-stage garbage collector for the AI short-term memory. Instead of waiting for the context window to be almost full and then doing a drastic, lossy summarization, ACC monitors token usage incrementally through 5 progressively aggressive reduction strategies.
So it's not a cliff, it's a slope. Exactly. At 70% capacity, it just logs a warning. At 80%, it starts observation masking, replacing older tool results with compact reference pointers. So instead of the full file content, you might just see output offloaded to scratch file. At 85%, there's a fast pruning pass that removes truly old and irrelevant tool outputs. Only at 99% capacity, as a last resort, does it resort to full LLM-based summarization of the conversation.
That's very clever. It prioritizes keeping the most recent and relevant information at full fidelity, much like how our own brains prioritize recent memories. And I can see how offloading large outputs to scratch files makes a huge difference. You don't need to keep the entire log of a 30,000-line build in the agent's active memory. Just a point or two is enough.
And it's not just about what to keep, but how, to ensure the agent remembers its core instructions over time. They observed instruction fade-out, where initial system prompts lose influence after 30 or more tool calls. The solution is system reminders.
Ah, the AI's equivalent of a Post-it note, right? But I assume it's more sophisticated than just repeating the system prompt.
Far more. These are short, targeted reminders injected exactly when the agent needs them, right before a decision point where it might otherwise go wrong. Crucially, these are injected as role user messages, not role system.
Why role user? That seems like a small detail but could have a big impact.
It does. After 40 turns, another system message might blend into the background. A user message, however, appears at the position of highest recency in the dialogue flow, and the model treats it as something that just happened, something requiring an immediate response. Their experiments showed user role reminders produce noticeably higher compliance rates. It's like a human getting a direct question from their boss versus reading a company policy document.
That's a perfect analogy. It's about leveraging the conversational dynamics of LLMs to maintain behavioral steering. So it's not just about managing the size of the context, but its quality and relevance at every step.
Precisely. And this careful context management extends to its dual memory architecture for the thinking phase. When the agent is deliberating, it doesn't get the entire conversation history. Instead, it gets a compressed, LLM-generated episodic memory of the full history for strategic, long-range context, alongside the last few verbatim messages as working memory for immediate operational details. This keeps the thinking budget bounded while retaining both the big picture and the fine-grained specifics.
That's a sophisticated design, mimicking how human memory works. It's impressive how they've tackled this fundamental bottleneck of LLMs with such creative engineering. But LLMs don't just have an attention span problem, they also have an imprecision problem. Their outputs are often approximately correct, which can be a huge issue in coding, where exact syntax and content matter. How does OpenDev design its tools to absorb this inherent LLM imprecision?
This is another area where the engineering is truly clever. Take the edit file tool, for example. When an LLM wants to change a piece of code, it specifies the old content to find and the new content to replace it with. In practice, the LLM's old content often differs slightly from the actual file, maybe a trailing white space, an indentation mismatch, or a slight reformatting. A strict exact match tool would fail constantly.
Which would lead to the agent constantly getting errors and trying to recover, wasting tokens and time.
Exactly. So OpenDev implemented a 9-pass fuzzy matching chain for edit file. This isn't just one fuzzy match, it's 9 progressively relaxed matching strategies. It starts with an exact match, then tries line trimmed, block anchor, white space normalized, indentation flexible, escape normalized, and so on. Each pass is designed to absorb a specific type of LLM imprecision.
9 passes. That sounds like an incredible amount of engineering to account for what might seem like minor differences.
It is, but it converts what would be a majority of content not found errors into successful edits. The chain short circuits on the first match, so if the LLM is exact, there's no overhead. But when it's slightly off, the tool intelligently bridges the gap rather than blindly rejecting the attempt. This is a perfect example of designing tools to absorb LLM imprecision as a first-class property.
That's a powerful principle. It's not about making the LLM perfect, but making the system resilient to the LLM's imperfections. And what about when the agent needs to find information? I imagine an LLM might just try to grep everything, which isn't efficient for structured code.
That's where their anchor-based retrieval tool selection comes in. Instead of a naive search, the system guides the agent to identify the strongest anchor in its query. If it's a symbol name, like authcontroller.validate, it routes to find symbol via LSP for semantic resolution. If it's a structural pattern, like all Python if statements, it goes to AST search.
So the agent doesn't just ask, find this. It asks, find this kind of thing using the most appropriate method.
Yes, and for more complex exploratory retrieval, it delegates to a specialized Code Explorer subagent. This subagent runs in an isolated context and can perform multi-step searches autonomously, perhaps finding a class definition, reading its file, then searching for its dependencies, all without cluttering the main agent's context window.
This brings us to another fascinating aspect, the idea of a compound AI system. It sounds like OpenDev isn't just one big LLM trying to do everything. How does this distributed brainpower work?
You've hit on a critical architectural insight from the paper. OpenDev is not a monolithic LLM. It's a structured ensemble of agents and workflows, what they term a compound AI system. The key is workload-specialized model routing.
Meaning different AI models for different jobs?
Exactly. They've identified 5 distinct model roles: an action model for primary execution, an optional thinking model for extended reasoning without tool access, a critique model for self-evaluation, a vision model for images, and a compact model for summarization during context compaction. Each can be independently bound to a user-configured LLM.
So if I'm doing something that requires deep strategic thinking, it might use a powerful, expensive model. But for just summarizing conversation history, it'll use a cheaper, faster one.
Precisely. This allows for fine-grained optimization of cost, latency, and capability trade-offs per workflow. The thinking model, for instance, operates without tool schemas to prevent premature action, encouraging deeper deliberation. And this modularity makes the system model-agnostic by construction. Adapting to new, better models only requires a configuration change, not a code rewrite.
That's incredibly forward-thinking, especially in a rapidly evolving field like LLMs. And it extends to human-like delegation, too, with specialized subagents.
Yes, the main agent can spawn subagents for specific tasks, each with filtered tool access and specialized prompts. Think of a Code Explorer subagent for read-only code-based navigation, a Planner subagent for detailed implementation plans, or even a security reviewer for vulnerability scanning.
And these can even run in parallel, so the main agent can effectively fan out work to multiple specialized experts simultaneously.
Correct. When the main agent emits multiple spawned subagent calls in a single response, the system executes them concurrently. This allows for parallel file searches, code-based exploration, or web fetches, and the main agent then synthesizes the results. It's a powerful way to leverage specialization and parallelism to tackle complex, multifaceted problems.
This paper really lays out a blueprint for robust autonomous AI agents in software engineering. If you had to boil it down to 3 to 5 core insights, what would you say are the most important takeaways for our listeners?
First, context is the central, finite resource for long-running agents. You must treat it as a budget, not a buffer, and employ progressive, multi-stage compaction and intelligent offloading to manage it. Second, safety is an architectural concern, not just a policy. Make dangerous actions structurally impossible through schema gating and defense in-depth layering. Third,
LLM imprecision is a given, so design your tools to intelligently absorb and correct for it, like the 9-pass fuzzy matching. Fourth, long horizon tasks demand a compound AI system with specialized models and subagents, each optimized for specific cognitive loads, rather than one monolithic LLM. And finally, behavioral steering is proactive and adaptive, not just about initial instructions. Event-driven, targeted reminders injected as role user are far more effective than static system prompts.
That's a fantastic synthesis. So, given all this, what's one question this work leaves you as a researcher?
I'm left wondering about the optimal balance between human and AI intervention. OpenDev supports approval workflows, but how do we design truly symbiotic human-in-the-loop interfaces that are both efficient for the human and maximally effective for the AI, especially as agents become more capable of long-horizon tasks? It's less about the AI replacing humans and more about the interface between them.
And for our listeners, I'd pose this. The concept of progressive degradation, where a system gracefully functions as resources are exhausted, is a core principle here. How might applying that principle to any complex software system, not just AI agents, change how we design for robustness and resilience in the face of unexpected limitations? That wraps up this episode of Paper Trail. Thanks for joining us.
Keep reading the fine print.